Jared, Jared, you're leaving us? Where are you going? Are you? Where are you heading? Sit down, pull up a chair. So, hello everybody. We're going to be starting in a minute or two. So, if people can find their chairs and sit down and stop shouting in the back of the room, that would be cool. Yay. So, hello everyone. Welcome to IEPG. Let me stop my laptop from making noise because otherwise we'll get feedback. So, hi everyone. Once again, welcome. This is the IEPG meeting at IETF 115. And apparently I found a slide deck with themes and stuff. So I got a little carried away with blinky lights and pictures of palm trees. So the IEPG is an informal meeting that happens before the IETF officially starts. However, we are still going to do things like require masks, etc., because it's in a IETF space, and also that just seems like a reasonable thing to do. We do have somebody here from Wide who is going to be taking pictures and filming the IETF meeting and IEPG meeting, unless anybody objects. Does anybody strongly object to pictures? Great, I did not think so. Chris Morrow is the other IEPG sort of chair type person, but I don't think he's online, so I'm going to be running all of the slides, etc. This is the first Meet Echo session of the sort of meeting type thing, so hopefully everything works fine. If we have any technical problems, just remember it's the first one. This is the agenda. This time we have a lot of discussions on measurement and things like that. Normally we have a lot of DNS and tiny bits of BGP. This time it's all day, every day, other than a little bit of Yang and also luckily some dot measurement. I have split things up somewhat so that we have some stuff and then a different discussion and then some more stuff and then DSCP and then dot. Does anybody have any agenda bashing or anything else that they strongly care about? Nope. Alrighty. I believe that the deep dive into is actually split into two presentations. I don't know who's actually presenting the first one. Is that great? Nyali. Okay, did not see you in the back there. So I will bring up your slide deck. Unfortunately, the little clicker thing does not do slide changing. So you're going to have to say next or this is the right deck, right? Or you can just push the right button on my keyboard, whichever you would prefer.
I'll just say next.
Okay, great.
That'll be fine. Okay. So, hi, I'm Nalini Elkins.
Microphones. There we go. Oh, it's got a funny like speaker. Right.
Who is that? So, starting over. Hi, I'm Nalini Better. All right. Okay, so I'm Nalini Elkins, and we are doing some diagnostics and troubleshooting for extension headers, and I will show you some interim results. We have quite a few people working with us, mostly from nonprofits here in the United States and India, as well as NITK, Surathkal, one of our fine Indian technical universities. Okay, next, please. So this is has been a controversy for quite a long time. I'm going to go through these first slides pretty quickly. There's been quite a few people saying extension headers don't work. Mhm. But it's kind of interesting because our own personal experience with testing some of our headers, which we want, which is the performance and diagnostic metrics extension headers, our anecdotal experience was that going across the internet, it did work. And so we were like, my goodness, I wonder what's going on. So, next, please. This is our extension header that we want to use for embedding in each packet to get real-time performance and diagnostic data. So let's go past that. Next, please. Our proposal for encrypting this extension header was accepted into the IAB workshop on managing encrypted networks. This is, of course, a very big problem. So what are we going to do as we do more and more encryption of networks? And our proposed solution is our performance and diagnostic metrics extension header. So this gave us additional impetus to try and make things work. So so this is kind of what we did last time. We set up various standalone servers at various points on the internet. And you'll see that becomes quite important, that they are standalone and they are with what I'll call a no-name server, which means that you're fronting right onto the internet. There's no intermediary between you and the server. And we, in this particular test, we had modified the kernel, the FreeBSD kernel, to go ahead and send tests. And you can see that we sent to locations throughout the world, passing through quite a few transit networks, internet exchange points, and so on. And it all worked. Next, please. And so thank you guys so much for all your help. Next, please. And you can see here, this is I'll go through this quickly. This is a large FTP, and you can see it all worked. This would happen to be Toronto to Mumbai. Next, please. And you can see that not only do we have our PDM extension header, our destination options, but we also have fragment headers all being transmitted successfully. Next, please. So bottom line, we have traces of everything. Everything's available to look at. So that brings us now up to the current time. Next, please. So then we're like, all right, let's see what's really going on. See if we can figure out, do EHs really work? And if they don't, then why? Why don't they work? So this is what our deep dive efforts are all about. And we have two drafts in V6 Ops, and they're troubleshooting techniques. We want to see, where is it blocked? Is it at the source? Is it the destination? Is it in the transit networks? Of course, depending on where things are blocked, the problem is easier and harder to fix. And then the other thing, is it intentional? Because interestingly enough, when we talk to some people, by that I mean some router vendors, some cloud providers, and some CDN providers, they were actually quite surprised to see that extension headers that we had isolated to their domain of control were actually being blocked. They're like, well, we don't believe we're doing this. Let's see if we can find out. So next, please.
Uh, Sorry, it didn't occur to me that if I logged in again, that would disconnect the session. If both versions complete.
Yep.
There we go.
Next. Yep. And so we have a side meeting scheduled where we'll have quite a bit of time to talk about our standalone testing. In this particular talk, I'm going to focus on content delivery networks. And the reason for that is many high volume sites use CDNs. And so when we did things like the top 1,000 Alexa sites, we could see that many of them were actually resolving to CDNs as one would expect. So next, please. So if we think about some topologies, what we have been testing where we saw things work were the very first scenario, which is very simple, which is you have a client, which is not necessarily behind a CDN, obviously, or behind any kind of cloud provider, just standalone going out onto the internet. And the same for the server. That's a very simple scenario. Of course, not that many situations fall into that arena, but actually, I mean, quite a few do, but many don't. What many high volume sites have something like this: you have your client wherever they are going out onto the internet, then they'll actually end up resolving to a CDN cache server, the closest one that's near to you. And then you'll do something, somehow you'll go in through the CDN network and then end up at your original server, which we will now call the origin server. And once you get into the CDN network, there may be very complex topologies, but this is the simplest scenario within a CDN. Then, of course, if you're on a cloud provider, that also becomes quite interesting. We will talk about cloud providers next time. Today, we'll talk about CDN. Next, please. So this is the very simple scenario. Let's go to the next one. So now we had that origin server, our original server, which we have enabled to send extension headers with every packet. You will recall that when we had it not behind the CDN, everything was working perfectly. So what do you have to do to move it behind a CDN? And recall, the reason we said, let's do this is because we could see that many high volume sites were behind a CDN. So we thought to ourselves, well, why don't we see what packets are getting through if we're on the other side of the CDN? So we just got free trial licenses or trial efforts with 3 different CDN providers. And basically, what you have to do is, first thing, you have to give the CDN authority to resolve your domain. So before, for example, if we had myehserver.com resolving to my original address of 2001::1, that's the standalone address, it will now resolve to the nearest CDN cache server. Fine. So I've given him DNS authority. And then let's see what happens. Okay. So next, please. So this is kind of what happens. You're no longer going to your origin server directly. You're being mediated. Okay. Next, please. So first thing is, what exactly did that CDN resolve to? And of course, we assumed it was the IPv6 address of our original server. Our original server has both a v4 and v6 address. And so we said, absolutely, that's what we're thinking it's going to do. And so we took a trace on both sides, because remember, I control both sides, the client and the server. In my case, the client is also EH enabled. So the client also sends an extension header with every packet. Next, please. So, huzzah. This is from the client trace. And you can see that I'm sending IPv6 data, grand, and I put a column called packet sequence number, this packet, that comes from our extension header. So, yes, our extension header is going through perfect because I got PSN this packet, but but it's only halfway. I'm only seeing it half. But I mean, one good thing, I mean, the packet isn't being dropped. I mean, so I am seeing traffic, but I'm only seeing EH one way. So I'm like, well, goodness, I'm really glad that I have access to the server on the other side and I can take a packet trace on the other side. Next, please. So let's go take a look at the server side. Next, please. And my first shock is, what? What have I done wrong? I am only seeing IPv4 packets. Okay, I must have done something wrong. And so, okay, next, please. So then I go poke inside the packet and I'm like, no, I did not do something wrong because in the HTTP, I can see that it is forwarded from IPv6. Also, too, I can see it is inside the CDN network. So I'm like, oh my heavens. So wait, what just happened? Next, please. This took me actually several calls to some of the people on the team saying, I must be going mad. Something has happened. Okay. So then I actually started looking at the documentation. My last resort, of course, is to read their documentation. And what they said is, well, if you have a V4 and a V6 address on your origin server, we will prefer V4 unless actually you go to a non-free, a paid service. I was doing free service and they want you to pay for the service and then we will change you to be able to flip and make IPv6 preferred. And of course, we are working for several nonprofits and do not have huge amounts of money. And so we said, all right, let's see if we can raise some money. No, I'm just kidding. So let's next. I shall tell you when to laugh. No, I'm just kidding. So, but but the next email, the next CDN provider, that was even worse because in that conversation, I actually first read the documentation. I shocked myself and I could see that they did not have V6 to the origin server. So I had a conversation with their tech support. And of course, the tech support was like, no, little lady, you are wrong. We do have support. And I said, okay, I shall send you some packet traces. And then they were gracious enough to respond back and say, okay, we read our own documentation. We actually do not have IPv6 support to the origin. And in fact, there's no current timetable for implementing. I said, my goodness, thank you for your email. Next. Yes. I had a very interesting few weeks here. CDN provider number 3, they are very, very cooperative and they are working very closely with us. And we've already found one bug in their network, which they are fixing and will roll out through their network. And now the rest of it was actually we ourselves had a problem. That there in some of these CDN providers, there's so many different options for which kind of service to test. We spend like 3 weeks after I picked the wrong service. But anyway, so now we are actually behind the server, and they indicate that V6 to origin is supported, but they do not believe that EH to origin is supported. And I am hoping that we will be able to work with them to support EH because we now have a VM image that we can quickly give to be able to test EH. Next, please. So, more breaking news. As it happens, we are now starting to test cloud providers. Newsflash, things are not looking grand. I will have more later. So let me turn it over to Anna. She's got a lot of stuff, and then I guess we'll take questions at the end. Yeah.
Thank Is every Does anybody object to the speaker taking their mask off? We generally allow it. Great, thank you. And just a reminder. Yep. Just making sure nobody objects. But also as a
Well,
reminder, everybody in the audience should have their mic on. I mean, mask on,
testing with the mask on. I think I'm just going to keep it on.
whichever you like.
Right. So are you ready for more extension headers? I have a good. I have a slightly different approach to that of Nalini, which is rooted in wide-scale traversal measurements. Next slide, please. Oh, yeah, and I'm Anna. I'm at the University of Aberdeen, where I specialize in internet measurement, and I'm currently completing a PhD on that topic. Right, so what I've tried to do with my extension header measurements is I've tried to focus on a wide set of diverse paths. So today I will be talking about what I've seen in edge networks. And I tried both sides of the edge. I've tried to test to the server edge, and for that I chose DNS servers and web servers in the internet. And I also tried to look at the consumer edge. And for the consumer edge, I made use of existing measurement infrastructure provided by RIPE. Next slide, please. Right, so I'll talk about that first. I'll talk about the RIPE experiments first. So what RIPE is, it is a distributed measurement platform. It has about 5,500 IPv6 enabled probes, and by probes I mean single board computers. I guess it is not strictly consumer edge because many of these computers will be in academic networks or in data centers, but a lot of them are, say, on mobile networks and in people's houses. Like I have a RIPE Atlas probe at home. So from all of these probes, then I've sent packets. RIPE allows you to send packets with either destination options or hop-by-hop options. And so far I've sent packets to 2 locations, but I've tried a range of different sizes as well. And I've also tried 2 different protocols, transfer protocols. RIPE allows you to do TCP, UDP, and ICMP, but I chose to focus on TCP and UDP. Next, please. So I mentioned that RIPE is globally distributed. This is a really cool image. This is the actual map of the actual probes that participated in the measurement that I'm about to talk to you about. So as you can see, it's a very diverse set of paths. Next, please. So what we learn, here's traversal at a glance. If you send the smallest, most inoffensive option that you possibly can, and that is an 8-byte pad N option, you get the following. You send it across the internet on all of these paths, and you try and work out if it makes it to the destination. Well, here's what you get. In the table for destination options, you can see that if you send packets with extension headers, with this extension header over UDP, it gets to the destination 92% of the time. If you change the transport and you use TCP, this drops to 68%. And then if you use hop-by-hop options, it drops a lot more, and you get 11% for UDP and 9% for TCP. But interesting to see here is that the difference in transport protocol is constant across, well, both of these types of measurement. Next, please. So next, what I try to do is I try to work out where the packets get dropped. So I've done a hop analysis and an AS analysis. And this slide is about drops by the first hop on the path. Next, please. So by first hop on the path, I actually mean the local router, the actual gateway of the RIPE Atlas probe in question. So what you can see here is a difference between hop-by-hop options and destination options. For hop-by-hop options, no wonder so very few make it to the destination, because the first hop on the path just blocks 55% of them, and that is irrespective of protocol. It just seems to be like a blanket ban on hop-by-hop options. For destination options, the story is slightly different. Not so many destination options sent over UDP get dropped at the first hop, but quite a few sent over TCP do. And this helps contribute to the difference in protocol that you saw in the previous slide. Next, please. Okay, there's a lot happening in this slide, but this is the per AS traversal results. Basically, it shows you at each AS of the path, on the path, how many of these packets survive. So you send 100% of packets with different extension headers. And for destination options, you can see that at the first AS, only 95% of them survive. At the boundary between the first and the second AS, that is to say where I couldn't determine where the drop was made in the first or the second AS, you still get another 2% dropped. And then I didn't continue adding more ASs because that's very close to the result at the very end, the destination, which is 91%. What you can see here is that the local AS is responsible for most of the drops, and this is to be expected because the local AS will see most of the packets after all. But I did not quite expect so many drops in the local AS, especially not for hop-by-hop options, where, as you can see, you get up to 75% of packets with extension headers being dropped there. I include more ASs in the table for hop-by-hop options because that's not the entire story. So for example, if you lose 70% of packets in the first AS, but then you lose another 10% at the AS boundary, then you lose another 5% in the second AS, and then you lose another 3% at the next AS boundary, and so on. So basically, the drops happen in multiple ASs and not just the local AS. Next, please. So then I decided to work out what would actually happen if the packets did traverse that first AS, where they get mostly blocked. And the way I did this is by, well, doing the same test, but in reverse. So essentially, I tested both directions because most of the RIPE Atlas probes have public IPv6 addresses. So what I have to do is do a trace route from the previous destination back to the RIPE Atlas probe. And because I have a control path, as I also send control, I also do a control test. I can exclude things like asymmetric routing or like ECMP from this measurement. And I can work out if the packet would make it back to the original S. So next slide, please. So in the case of destination options, actually, it turns out packets do make it back to the original AS. So essentially, if you would exclude drops that happen in that first AS, you could bump the traversal up on this set of paths to 96%, and that's great. For hop-by-hop options, however, you don't get that many packets making it back to the first AS because they seem to be getting dropped in transit or in other parts of the path. So this is, I guess, is to be expected because we saw that the traversal for hop-by-hop options is overall a lot lower than for destination options. Next, please. Now this is the fun slide of, I mentioned I sent packets with different sizes, and I tried to work out whether there's a difference in between TCP and UDP with respect to how big a packet can you send. And I found a difference. You can see that TCP sees the biggest drop in traversal at 48 bytes, and UDP sees the biggest drop in traversal at 56 bytes. So they are shifted by 8 bytes, presumably because the size of the transport header is different. TCP is bigger than UDP. But I think the key takeaway from this slide is that if you send an extension header of 40 bytes in length or less, then you have the highest chance of it going across at least edge networks. Next, please. How are we for time? Okay, okay, cool. So then I can speak a little bit about the server edge, and I think this is fun because it ties in with what Nalini just presented. So this is an entirely different experiment, right? It's not a traversal experiment. It's more of a functional experiment. So can a packet with an extension header function just as well as a packet without that extension header? Essentially, I'm sending the packet to the server and seeing if I get a response back. The packet in this case was a DNS query. And I chose DNS here because of two reasons. One, you can send queries over UDP and TCP, so you can test both protocols. But then also, the DNS, so these servers, they are essentially the authoritative NSs for the domains in the Alexa top 1 million. So if you look at the list of web servers for those same domains, you'll see that most of that is just Cloudflare. And at least the DNS list is a bit more diverse. Still, you still get like 15% of this of all of these destinations being Cloudflare, but it's a lot less than if you were to choose web servers. So that's why my targets for DNS servers. In total, there were like 20,000 of them. So I tested UDP, TCP, destination options, and hop-by-hop options. And also I tested a few things. I varied a few things in the header to see whether or not it affects traversal. So for example, you can test with a valid 8-byte pattern option, but you can also test like an unknown option or like an invalid length and see what happens. Next slide, please. Okay, so we have some numbers here. Remember that this is a functional test. So the 53% you see for, say, destination options just means that 53% of the servers at the other end responded to our query. And remember that the data set is made out of a lot of, servers in CDNs. And we saw what happens in CDNs in the previous presentation. So this shouldn't surprise you. We also see a very small difference between TCP and UDP. It's not as large a difference as you could see in the Edge dataset. And I've tested these 20,000 paths from 12 locations for destination options and 3 locations for hop-by-hop options. Only 3 locations because actually I struggled to find providers that supported them. So I struggled to find vantage points from which to test in because of the lack of support for hop-by-hop options in cloud providers. Next, please. Right, so I mentioned CDNs. Well, here are the top ASs that essentially do not pass destination options. And by do not pass, I mean either they drop them or simply do something in the background and then the packet you send never gets a response. And as you can see, we have the usual suspects: Cloudflare, Amazon, Microsoft. But if you did fix the CDNs, you could get your traversal up, not traversal, sorry, your response rate up from 50% to almost 90%. So that's something to keep in mind. Next slide, please. And finally, I think I mentioned, I tried to vary the different types of fields. Okay, so this is what an 8-byte option looks like. This is a pattern option. It looks the same for destination options and hop-by-hop options. And I tried different things in different fields to see whether or not this would help traversal or if it makes packets get dropped differently. So what I found is that for this specific data set, if you send an invalid option type or a fake option, as Nalini called it, that doesn't make a difference. The traversal stays the same as it is. What I did find that did make a difference is if you advertise an invalid extension header length or an invalid option length, that immediately leads to like almost 100% drop rate. And I guess this is to be expected. But those fields are the fields that I think routers check, and the rest of them, they don't make too much of a difference. Next slide, please. So, in conclusion, well, we learned that destination options, at least, they currently travel quite far along a path in both of the datasets that we've seen. And we've also seen that there are still some types of networks that drop them. Whereas for hop-by-hop options, a very diverse kind of set of paths, edge networks, as in consumer networks and CDNs, drop these guys, and even transit networks, they drop packets with hop-by-hop options. But you still have a few of these paths that support them, and that's a positive. And finally, we've seen a difference in transport protocol. And I have some theories as to that, so please speak to me after the presentation if you're interested. Next slide, please. Yes. Question time.
Excellent. And we've got a total of 6 or so minutes for questions, so please keep the questions short.
Can I get Can I get Nalini as well here? Just in case. I don't want to answer the hard questions by myself.
John Border, I have a clarification question. When you were doing the UK traversal from the edge, is the first AS the same AS all the time? What I'm really wondering is, does a given AS always drop it, or does it sometimes drop it?
So the first AS was the local AS to the RIPE Atlas probe. So the first AS was always going to be the AS of where the probe was, not
So
of the UK
it wasn't
destination.
necessarily the same one in every
Oh no,
probe. Okay.
they were all different.
Jelinkova. Oh my God, it's the best IPG meeting so far. Thanks for the agenda. 2 questions. One really quick clarification. When you showed the first IS and subsequent IS drops, in that
Go back to the slide.
yeah, in that drop you include the first hop drops, right?
Yes, I do.
Okay, so did you look at how better result would be if you exclude the first hop drops? Because in my measurements, I feel like a lot of that stuff is dropped by cheap CPs.
Mm-hmm.
We just have no idea what to do with all those strange fields.
Yeah, so I'll answer your question in 2 ways. So if we go back to the slide for one more, and then the previous one to this one. So I guess the first hop on the path drops, like, say, for hop-by-hop options, 55%, and then in the first AS you have 75%. So the difference there is 20%. So you can calculate it that way. But what I did do is I had a look at these CPEs, well, of the of what this first hop on the path does, and I tried to cross-reference those machines that also do things like modify the MSS field. So I try to work out if they're middle boxes, and I try to work out if that influences the traversal rate, and it does. So if you have a middle box in the path, the drop rate is much, much higher for those paths that have middle boxes on than for those which don't. I don't know if that answered your question.
Yeah. And a second quick question. So because you look in the average, you're saying like 20% dropped between first and second IS, for example, right?
Yeah.
So am I right that in most cases you see some ISs dropping 100% and some of them 0, and it's not really likely to see like dropping random number, right?
Absolutely.
So it's more like all or nothing.
Yes, absolutely.
By the discretion of the chair, may I?
Yeah.
Okay. Hi, Tail. I couldn't
Hi.
join the queue because weird Midako stuff. But rather than everybody having to ask you afterward, can you tell us your theory on the discrepancy between TCP and UDP?
Okay, so I did touch on this in the previous question. For one of them is that you have loads of devices in the past that will modify bits of the transport protocol. So you have, I specifically looked at boxes that modify the MSS option sent for TCP in order to help with path MTU discovery. And I noticed that that makes a difference. So that's one of the reasons. And the second one my theory is that it's of course firewalls, which look more at TCP than they look at UDP. And I plan on testing that somehow. I'm yet to concoct my amazing firewall test, but I will, and then I will present the results.
Thank you.
And we have time for one more short question if anybody has a very short. Nope. Okay. Thank you very much. I think this was great. And now we have something that is not EH. If I can find the right slide. There we go. I believe that this is Thomas, and I think this is 20 minutes. So I will put up a clock, and that's what the questions, obviously.
Thanks a lot. So yeah, today I'm Thomas from Swisscom, and today I like to show you some challenges we have with the network telemetry data mesh integration, specifically, yep, sorry, specifically on Yang push. Next slide, please. And before starting there, just to give you some insights like how we are using network telemetry metrics. So here in this example with network anomaly detection for layer 3 VPN, we are having actually two VPNs, so blue and orange, and one of the two VPNs, the blue one is redundant, where the orange one actually is not redundant. And we are looking from different perspectives in the network. So on one hand, we are monitoring the BGP updates and withdrawals. On the other hand, we are monitoring on UDP and TCP the missing traffic. And on the last one, on the interface state changes. And you see on the left side at the top, we have a so-called maximum concern scoring, which is basically accumulating all the concern scores we have. Then further down, you see the BMP measured BGP updates and withdrawals, while further down, the IPFix measured flow count on TCP and UDP, and on the very last one, the Yang push measured interface state changes. And while on the first event, basically, we see that we have some on the blue VPN, some updates. We have withdrawals just on the on both on the orange and the blue one, while from the forwarding perspective, orange is now dropping completely. Blue is unchanged because it's redundant, and the interface state changes we have for blue and for orange. While when we move on to the second event, yep, not yet, previous slide. So on the second event, so the red line in the middle, you see basically the overall concern score now is going up for blue as well. And the reason is that we are no longer forwarding for blue. We have some BGP withdrawals in the network and also some interface state changes. So you see with this example, we have to look from different perspectives in the network to get an overall picture how the changes in the network are actually affecting the forwarding of the packets. Next slide, please. So from a network operator perspective, what we are aiming for in network telemetry is that we have at the end an automated data processing pipeline, which starts with network telemetry, where we are collecting data from the network. We consolidate the data in a so-called data mesh, which I will explain later more in detail. And on top of it, we have network analytics where we can gain insights on those metrics. And from a semantics point of view, so the IETF defines the semantics for the operational metrics, while the analytical metrics are generated with the analytics capabilities at the network operator. We achieve this goal by actually forwarding the metrics from the network unchanged. We are learning the semantics from the network, and thanks to the semantics, we can also now validate the correctness of the messages, and we want to control the semantics. So we want to make sure that when semantics are changing, that we keep the backward compatibility in control. So we say, so we can actually move to new revisions of the semantics. Next slide, please. So state of the union, I'm paraphrasing here, but today, and I will explain why, we have a bit of a mess, I would say, in terms of how we get ordered the metrics from the network. And the data mesh is basically the next generation big data architecture, which is quite already advanced. And next slide, please. So some introduction on the big data architecture here. So it evolved over time. It started with proprietary data warehouses, it went to centralization into big data lakes. We added with Kappa some maritime streaming capabilities, and now basically ending at data mesh. And from a network engineer's perspective, data mesh is much like how we are managing our networks today. It's distributed. We are dividing them into different domains. So at the end, we have many different teams managing their part of their data. And of course, in order to exchange data the proper way, same as with networks, we need standardized interfaces, and they're called in data mesh bounded context. And the data mesh architecture actually defines that within an enterprise, the operational metrics should be standardized with a federated computational governance. But since here in network telemetry, we are actually collecting the metrics from networks, and how IETF take the responsibility to standardize the semantics there. So next slide, please. Looking now on the Yang push size and looking at the different, let's say, angles on Yang push, on transport, encoding, subscription, metadata, versioning, and the Yang models, and comparing what we have today on the network operator side and what we are developing at IETF, what we achieved there. We can see on the transport side, pretty much different non-standardized Yang push transports. Then at IETF, we have with HTTPS notif and UDP notif drafts which are close to ISG, getting into an RFC. On the encoding side, also, again, different encodings in the operator. So we have JSON widely. If you go into binary encodings, we see protobuf in most cases in various variants. CBOR itself not yet implemented, while at the IETF side we have JSON, XML, and CBOR already in RFC. On the subscription side, same again, very much at the operator side, it's non-standard. Periodical subscription are widely adopted, on change seldomly. And at IETF, we have two RFC describing very well the subscription side. The metadata, there we see also that basically it's within the JSON message itself. So it's very hard to find out what part of the JSON message is actually the Yang model itself, and what part is actually the metadata. And now at IETF, we are starting with these drafts here to describe the metadata more properly, so that we have a semantic reference towards the message which we are transporting. Then on the versioning side, I would say there it gets really, on the operational side, we have nothing. While at IETF with NetMod Yang module versioning, we are working on semantic versioning on backward compatibility. Regarding the Yang modules itself, at IETF we have many RFCs. So, and looking what's currently being implemented, I would say that the coverage is very sparse. So that's the situation which we have, and that's why I mentioned before, we are actually going from a, let's say, a messy situation towards a more organized situation, but we still have some tasks in front of us. Next slide, please. So where we are heading to. So at the end, in a nutshell, basically, we have the network, we have the data mesh, we are pushing configuration through an API, through netconf, resconf into the network, and through Yang push, we're getting the operational metrics back. So it's basically just in the future, a simple cycle between network and data mesh. And in order to bring these two worlds more closer together, because today big data doesn't know much about networks, doesn't know much about semantics, we are now collaborating with different operators and network and analytic providers and universities together, and kick off here a project in a side meeting on Monday afternoon, if you have interest to join us, so that we can ease this integration between the two worlds better. Next slide, please. So in a nutshell, data mesh is a big data architecture. It relies on bounded context. So we can forward semantics. So basically, Yang push is a message protocol. Apache Kafka is a message protocol. And what we are trying is actually to make sure that this integration between the two worlds are much more easier. So we are bringing Yang, the semantics into the schema registry, and we are extending Yang push so that we have the semantic reference. So when we learn the message from the network, that we can actually retrieve the Yang module, the schema from the network node, register it into the schema registry, and push then the message into the Apache Kafka message broker so that we have a semantic reference with the aim at the end, before we are ingesting it into a database, that we can actually obtain the semantics, create the ingestion specification, and then ingest the data into the database. So at the end, it's about an automated onboarding of data. So a network engineer can simply configure a new XPath, and a minute or two later, he sees the metrics in the database. Or in another way, simply now different domains, different products can actually exchange data in a data mesh. And that makes integration much more easier. Next slide, please. So this is just one of the puzzle pieces. So where we actually extend the subscription mechanism in Yang push, and also extending the metadata in Yang push. So at the top, you're seeing basically what additional information we are adding into the Yang push meta, mainly the reference to the Yang module, the revision label for the semantic reference, and which XPath or sub-tree filter we have been using. While at the bottom, giving the capability not only to subscribe to an XPath, but actually also subscribe to a revision or a specific revision label. So when you're upgrading the node, you're not breaking the end-to-end data pipeline by going into a version which is not backward compatible to the existing one. Next slide, please. Here, the example in a JSON and XML message with the semantic reference. Next slide, please. Do you realize the gaps and how it can be resolved? Adding semantic reference in Yang push and in data mesh, we can enable automated data processing pipelines, can do the integration between network telemetry and data mesh by collaborating with different operators, network and analytical vendors and universities together to bring these semantics into Apache Kafka, and adding semantic references into Yang push. I would be interested to hear your thoughts and comments. And if you want to learn more, please join us on Monday on the side meeting at 1:30, or below there is a link giving you additional details on the project itself. Thanks.
Questions? Nope. Okay. Excellent. Thank you very much. Next, we have Jeff Houston on another IPv6 extension header measurement using a different methodology. And while Jeff's coming up, I will remind everyone that there's the technology deep dive session tomorrow morning starting at 8 a.m. And
Fine to pack, Warren. Hi, my name is Jeff Houston, and this is work with Joao Damas from APNIC. So we're back to the wonderful world of IPv6 extension headers again. You thought you might have escaped it, but you were wrong. Next slide. This kind of came up in 2016. And for me, I must admit, it was the right-hand column, because this work, Jen Makova, Fernando Gont, and a couple of others, whose names I have forgotten, but you can look up 78, 72 as quickly as I can. What it really said to me is V6 can't fragment. With that kind of loss rate, you cannot fragment packets through the internet and make them work, which is for the DNS and V6 a death knell. You just can't make big packets work if that's the loss rate that's real. The other ones were, you know, well, who uses it anyway? Curious, but little more than curious. If I read the documentation in that RFC correctly, they were using pad-n and they were padding the size of the header up to a total of 8 bytes. And we'll see why that's important a bit later. But this was also client to server, not server to client. This was the opposite direction of most of the bulk of the traffic. So they were sending crafted V6 packets within a TCP session to a bunch of servers and 2 sets, the World IPv6 Day set and the Alexa set, and seeing what they got back in terms of, you know, if I sent a SYN packet, then who sent me a SYN-ACK, that kind of work. I'm not sure exactly what packet they used, but the principle was client to server. Next slide. Oh, and by the way, the fragmentation, back one, again, that's going to be important, was 2 512-byte fragments. So it was a single point test, and we'll see that that becomes important. Next slide. So we got curious about this a couple of years ago and decided that we would push this a little harder. And using a mechanism that was fundamentally different to Atlas, we actually used a couple of Linode boxes and created a very standard back end. So here's, you know, Nginx running a web server, yada, yada. But in front of that, we actually put a V6 NAT. And the way it worked is the front end accepted incoming packets, changed the addresses so that, you know, the return from the web server got back to the front end box and just sent them inward. But it also created a binding and a flag of a transition to apply to the outbound packet. The outbound packet got back to the front end server, and we then diddled and played with that packet. How do we do that? Well, the thing is running standard PCAP packet filters. So it's picking up every packet, and we actually send raw IP. It's a totally synthetic packet that we send out the other end. It looks like what the back end did, but we've added either fragmentation or extension headers. Now, we wanted to test a whole bunch of things without doing a whole bunch of experiments. And because we're using an ad-based measurement technique, we have around 26, 27 million raw sample points a day. And so we could conduct a whole bunch of experiments simultaneously. And the way we did that was every single time we found a new TCP session, we randomly flipped the coin and selected a test. It was either fragmentation to a certain packet size or adding a HBH header to a certain size or adding a destination header to a certain size. So simultaneously, we were doing around 54 tests across those experiments all at once, which meant basically a large amount of data was being collected. These are ads. I'm not normally testing servers unless you're running Apple's private data relay. I'm actually testing statistically mobile phones, but a whole bunch of other things as well. You know, what's behind a broadband network, possibly smart televisions, who bloody knows, I don't. But we're testing end devices. So this is the opposite of the earlier work in 78, 72. This is all about servers to real clients, right? So it's the mirror image. Next slide. I just said all that. That's roughly what we tested. We're not using pad-n. There was an experience in using pad-n, which was disastrous. We're using the 0x1e type code, which is evidently reserved by IANA for this kind of experimentation. And we're doing basically a progressive size of, you know, 8, 16, 32, 64 for each destined header. And the fragmentation, not 2 by 512. We're actually moving around that 1280 point of doing in 8-byte hops the initial fragment, 1200, 1208, 1216, up to 1416 octets of the initial fragment size. So all that was being tested at once. Next slide. So this is the first result, and I've normalized the vertical axis across all these slides to give you a feel. But I must admit, there are certain points where the eyebrows raise. There is no known reason that I can think of why the drop rate is higher once you get to about 1360 octets in the initial fragment size, but it is. And there is no reason that I can think of why 1416 is higher than the others. No reason I can think of. This is everybody. Next slide. But the internet isn't everybody. The internet's bloody weird. Here, is this part of Europe now? Okay, a little further west, you know, somewhere, or east, sorry, somewhere that is Europe. If I look at Europe, oddly enough, the larger fragments actually have a lower drop rate than the smaller initial fragments. So over in Europe, the number goes down slightly, not up. In North America, it goes down but stays steady. Bizarre. If I look in South America, predominantly Brazil is the major contributor to V6. 1416 is just evil. You know, do not pass that packet, but all the others are cool. Which, again, I have no idea why. And don't forget, we had adjusted the MSS. These were packets which in theory were going to make it. I'm not pushing beyond what was the initial MSS value. And in Asia, you again see this peak at the high packets. India, which has a massive V6 rollout in Reliance Jio, is the major contributor to that behavior. That the larger initial fragments have a dramatically increased drop rate compared to the others, because there's all these vertical sizes are the same rate. So for small fragments, India is doing magnificently, much, much better than, you know, Europe, North America, South America, except for big initial fragments. And China abandoned all hope, but the bigger packets go abandon even more hope than you ever had, and they wouldn't have any hope anyway, so it's all just stuffed. So why does it vary like that? Next slide. Is it the fact that there's a header or the fact of fragmentation? So we included a test that says, here is a packet with a fragment header, but the fragment header says the entire packet's here, an atomic fragment. And again, the world average, about half of the fragment drop rate. Cool. Next slide. Whoa, United States? Curious. You notice this really solid weekday, weekend packet drop rate in the US, that during the weekdays, the fragmentation drop rate is slightly higher than weekends. Maybe there's an issue about enterprise networks and the way they do firewalls. But the atomic frag drop rate is constant weekday and weekends. And it's about the same order of magnitude, you know, somewhere between 7 and 8%, right? Look at China. Fragments are evil. Atomic fragments, at least in the last 2 months, are highly fashionable. Before then, they were evil, but now they're not evil anymore. Next slide. I have no bloody clue. You might, but I don't. Okay, so that's frags. Next slide. Let's move on to destination extension headers, the ones that are meant to pass through the network and only go to the box. Now, most of you run a variant of Linux, no matter what. You know, Microsoft or whatever they used to do, Windows is basically dead. There are very little out there. And most of you use code that has this particular piece of code in it. And it says what it means. If the padding option is there, pad n is only to bring it to a size of 8 bytes. If it's bigger than that, drop the packet. And if you're padding with anything other than zeros, it's bad. Next slide. Now, we didn't read that. So for the first few months we were running this experiment, we were running with pad n, all ones, and sizes of 8, 16, 32, 64, and 128. And we were getting bad. We were getting bad because we're padding with all ones. And if it made it through the network, the host just dropped it anyway. Ninda. After doing I think it was after the last IETF meeting, and someone kindly pointed out that piece of code, thank you, we then found the following results, which are kind of interesting. 128 bytes is more evil than a smaller destination extension header, which tends to suggest something closer to the network than the host. And interestingly, 64 bytes is more evil than lowers. 8 and 16 are largely the same, and 32 byte is slightly different. Averages get confusing. Next slide. Because in Greece, it's really, really low. 128 byte headers have a higher drop rate than the rest, but in absolute terms, they're both tiny. Whereas in the United States, destination headers are evil for almost all networks, and the 128 byte headers have a more higher drop rate than the others. I thought it was all Cisco and Juniper gear. I thought we all ran Android. In a lot of the work on experimentation on the network, we kind of assume that everyone runs the same vendor equipment and much the same configuration because you guys travel all around the world and offer all of your ISP clients the same config. And so we always assume that the world is painted the same. And when you find these kinds of differences, I'm like, it's not that you're running a different version of Android in your handsets. You're not. The networks are being treated differently. And don't forget, this is an ad-based experiment. We're following where eyeballs are. Next slide. So you do the world map, and what you find is, again, sort of if I look at countries and the average destination drop rate across all sizes, the US fares much worse than others. Brazil better, China near, Australia bad, etc. UK pretty bad. Next slide. And I kind of wondered, is it something to do with broadband and CPE versus mobiles and no CPE? I'm like, the CPE is buried deep inside the provider network. And there is something there that T-Mobile in the US has a much lower drop rate than Comcast in the US. What you actually find is that landline-based systems, which are more reliant on the CPE to get the destination header through, seem to fare much worse than mobile systems. You also notice with Comcast, 128 bytes, near, same drop rate as everything else. Whereas in T-Mobile, it just pushes up ever so slightly. So there is a difference between mobile and fixed. Next slide. Okay, that's as much clue as I can offer. Let's move on to the last one. Time is running out. Same problem. We were doing all ones pad N, so everything was getting dropped. Oh, we'll outsmart this. We'll go to 1E1. Everything gets dropped. Absolutely zip change. That's almost 100% for every size. Next slide. Everybody everywhere drops everything where there's V6. The bits that are white, there's not enough V6 to test, but everywhere else, it's bright red. Now, one or two reasons. One, it's them. Two, it's me. Because if something is dropping something 1 inch away from the server where we're emitting that packet, obviously the world looks red because the drop happens, you know, just there. Next page, next slide. With one exception. The one that proves the packets are making it out of the server. Because there's one provider in Egypt, Etisalat, that doesn't have a 100% drop rate. Does not have a 100% drop rate. It only has an 80% drop rate, except for one size, which is higher, 90%. And what's that one size? You can't tell, but I can. It's 16 bytes, not 128. For some reason, a 16-byte destination header in Egypt is evil, but everything else is less evil. It's still 80% evil, but not 100%. But what that does prove is the packets made it out of the data center. And in this case, the data center's in Frankfurt? Yeah. So made it through Germany, got across the Mediterranean, yay, and died in Egypt. So we can assume that most of our packets made it out of Germany somewhere and made it into the transmission systems and then got killed somewhere else. It's not us, it's them. Next slide. So what can we say? We don't know what we're looking at because we're looking at the interaction of a whole bunch of side effects that are extremely difficult to understand. Because what particular V6 transition strategy you're using appears to have a real effect. T-Mobile 464XLAT has a much lower drop rate than, say, Comcast, which is fixed, using, as far as I understand, DS Lite, and someone can correct me if I'm wrong there, but it's a different kind of transition strategy, which appears to have a bearing on the way these V6 packets with extension headers are being treated. So whatever ISP equipment you're using, Less so, because in some ways the world runs the same code. Even Huawei, the world runs the same code. What CPE you're using will be different, because CPE is crap in so many unusual and inventive ways. And everyone is crap differently to everyone else, because you guys are engineers, not creative artists. So when you're asked to be creative, write a new CPE, you usually get shit instead. You get it wrong in different ways all the time. And that's what we're seeing. CPE is never consistent. What mobile platform you're using, and not what handset, but what they're using at the other end makes a difference. And private relays and proxies, which with Apple's move and Google's move in this area of increasingly sucking everyone into Google Fi or Apple Private Relay, has a real big effect on these kinds of measurements through to the client. Because you're now seeing the interaction between the front-end obscure system from client to sort of public interface, and then from public interface to where we are. Or have a different reason, you know, invent your own. Next slide. I think I said all that, but what I would say is there is no single answer. So what this means, if you think you can rely on EH getting through as a code developer, you are wrong. It might work or it might not. And the context of where it's being used has a much greater bearing than the particular EH option you're actually using, right? So it can't be relied upon is the real message. And that includes fragmentation. It can't be relied upon to work everywhere all the time. An HBH is dead, except if you're, you know, behind a Telesat in Egypt, and then it's only slightly dead. Yay. Don't use it. Next slide. Thank you. Questions? I think I've got 2 minutes and 34 seconds.
Jan Linkova. Thanks, Jeff. Very stupid question. When you see that drop rate increases with the size, you have a spike, right? Do you, if you see unfragmented packet of different sizes, do you see any drop spike there? Because I'm thinking about MTU somewhere.
I am in the middle of a TCP session, right? And I've actually got a client, same server, same client, where I'm not going through the front end in any case. I've already set up an experiment context. This is not the first time that server has talked to that client in V6. The conversation that set the experiment up, not being measured, separate TCP conversation, is not being, if you will, diddled and deliberately fragmented. So I know that normal packets in V6, including a TLS extension, big packets, are actually making it through. Otherwise, I'd never have started the TLS extension, you know, the TLS handshake would never have completed. So I have a fair degree of confidence, and I haven't actually gone through and gone A-B comparison on every one, but I have a fair degree of confidence that this is not, that person is uncontactable. This is saying, when I deliberately fragment the packet, I can't see any more ACKs. That's where it goes bad. So not a stupid question, very good question, but no, it's not due to the fact that they don't like any packet at all. They really don't like frags.
Excellent.
Hi, Jeff. Really a lot of great data. Thanks for doing this. What I'm taking away is there's a lot of unexplained situations and a lot of unanswered questions. What do you see as the next steps for maybe pursuing getting some of those answers?
Well, if you think EHs can be made to work, I'd love to be as optimistic as whoever thinks that. I have no such optimism, point one. Point two, if you think you can make fragmentation work in UDP, good luck. I don't share that optimism. So what this really means is that unless you truly understand not just the two ends, but the environment in which you're hoping for this to work, you can't count on an arbitrary environment working, and you can't hope to fix it. It's gone, it's dead. You might be able to salvage a point-to-point out of all of this, but that's not assured until you try it. So the EH story in V6 is mostly dead, But if you search for signs of life, you might be lucky in a particular config, but that's not the general rule.
You said some pretty bleak things with a smile there, but if
What else can I do?
I know. Yeah. Keep your attitudes up, right?
Thanks, Dave.
But if we do try to solve some of these things, is the IETF the right place to do it?
We're getting to the point where the deployed massive V6 has its own bleak implementation stasis. And the amount of crap CPE out there is now an irredeemable problem. The amount of operator, I'm being driven by contractors and what's in the box and I have no idea what I did yesterday, let alone what I did 2 years ago, says it ain't going to get fixed. We have to live with what we do. What does Quick do? No packet bigger than, I think it was 1340 at one point, and these days it's 1200. So Quick is actually going, I don't care about fixing this. 1200 works. And I can really understand the pragmatism that's gone into that thinking. Instead of trying to fix, the elephant, just simply go through a path that gives you a much higher assurance of success and forget about the rest of the problems.
Thanks again. One more quickie. You mentioned something about Windows doesn't apply or doesn't.
Hardly everyone runs it. That's all. We're talking highball systems. Windows is dead. That's all.
Yeah, I can only say that in enterprises that Windows is huge.
Well, in the ad
especially on
system,
clients.
in the ad system, either they don't get ads, interesting, or they're not really running
Okay,
Windows.
so they're not used in your testing scenarios.
They're not used where ads go. Eyeballs. Different question.
Okay. Thank you again.
Thanks.
Thank you.
Better be quick. We're running out of time.
Yeah, one more question. So very interesting data. So from how many servers did you do your test and to how many clients? Sorry if I missed it and it was in the slides.
Number of servers is currently 6 at points around the world. They're all Linodes, so they're all running inside Akamai. Number of clients, the Google ad system is truly prolific. It tries like crazy to deliver 28 million new endpoints every single day. I don't retest the same people. I just test whoever Google throw at me, and Google are bloody good at giving me, at this point, just under 30 million new clients every single day.
And do you have any idea in how many ASs overall you've tested?
All of them.
All of them.
Have you seen an ad? Hands up everyone who's seen an ad.
There
you go. It's as big as that.
Ad blocker, but
no, but realistically, from the Faroe Islands right through, we see everything. Everyone has ads.
I would be very interested to see the split of ASs, especially because
They're on the web pages. I can show you where all the web pages are. That tell you all the sample rates per AS.
Cool. Awesome. Thank you.
We're done. Thank you.
The other one of yours. I think you're up again. Sorry. DSCP.
Oh, it's me again.
Yep.
Hi.
That one.
Yes. Hi again. I'm going to switch context for a bit, and now we're going to talk about the magical world of differentiated services code points. So a bit of context for this, I gave this presentation in TSVWG at IETF115, and then it got picked up by Bob Hinden, who suggested that you lot might be very interested in these measurements. So here I am presenting it. It's the old slide deck. It's got some. It's okay. We can go through it.
Okay.
It does have a bit of some animation glitches, right? But I'm about to present to you some data that underpins this draft that I have in DSVWG called Considerations for Assigning DSCPs.
If you want to wait, I can click refresh in case the new ones. I uploaded them. They might not have.
Okay.
The theory is that they refresh button. We uploaded them, but did it actually process them? We will find out. Share. Is this the new ones?
The title is still the old one.
No,
That's
looks
okay.
like it's not. Oh well.
That's fine. Cool. Right. So some background about differentiated services code points. Well, they exist. They live in the IP header. They are a differentiated services code point is a essentially a value defined in a 6-bit wide field. And it can encode the value between 0 and 63. And these values basically are looked at by other routers on the path, who can then provide quality of service within a diff-serve domain based on that particular, sorry, I think you skipped one slide ahead. Yeah, more context here. Right, so routers on the path essentially look at this field and they can modify this field and they can provide quality of service treatment according to this value. Now we have a diff-serve field now, but before 1998, what we used to have is a toss byte, and in the toss byte you had 3 bits, the first 3 bits, called the precedence field, and that was used in order to do the same thing. This is important. Next slide, please. Well, what happened in 1998 is that RFC 2474 came along and said, right, guys, we're no longer doing IP precedence. We're now doing diff-serve. If you implement diff-serve, you will be looking at this 6-bit wide field, and you won't be looking at the previous 3-bit field. And in order to provide backwards compatibility, it essentially defined some new DSCPs that are called class selector DSCPs, and they keep compatibility in the following way. Essentially, it's all of the 8 values that would have been encoded in the IP precedence field, and you take all of them and you stick 3 zeros at the end, and voila, you have your DSCPs. Next slide, please. So DSCP did take off, and here you can see all of the code points between 0 and 63. They are arranged in an 8x8 grid, and I'm going to show you on the grid which values have been assigned. Next. So I mentioned IFC2474 defined all of these class selector code points, and they are assigned. Next. Then in 1999, 1 year later, you start getting all of the assured forwarding code points, which also encode drop precedence, and they are assigned. Next. Then along comes EF, I think in 2001, and voice admit 10 years later, roughly in 2010, and then even 10 years later, you get the latest allocation of lower effort, which is code point 1. Next. On top of this, you also have some code points that are reserved for experimental and local use. Basically, if you take the binary representation of the code points I've just shown in red on the slide deck, you will see that they end in 1-1. And that's why they are on those 2 columns. And these are the reserved ones. So here's what the grid looks like. Next slide, please. Now, out of all of these allocated code points, which ones are used? Is what I'm about to tell you. And how do I know this? Well, I know this because I've been doing measurements with differentiated services code points ever since 2015. And I've looked at many different data sets. Next, please. So for example, by examining web server replies, you can see that they use the very popular short forwarding code points, AF11, AF21. Some of them use CS3 and even EF. Next. By doing trace routes within mobile networks, you normally see there that the mobile networks like to remark all of the incoming code points to a single code point. Normally it's B, but you also see AF11, AF12, and AF13 being popular choices that are used within mobile networks. Next, please. We've also looked at passive data traces collected by CADA, so like very large pickup files. And in there, we saw that, for example, ICMP traffic often uses CS6 or code point 48. This is in line with RFC 2474. So that's being used. Next. And then finally, by examining DNS server replies, you see they like to use code points like CS1 or CS4, and again, AF11. See, AF11 seems to be a very popular one. As I've mentioned, this is all measurement data. I've put some slides in the appendix for you. You can have a look at, but also I'm linking to the conference paper and the journal paper that I've published at the time with this. Next, please. So I'm gonna say next again to avoid the bug. And one more, yeah. Some of the colors disappear. Right. The measurement data also shows a different problem. I've mentioned the precedence field, and well, it turns out that there are still many routers in the internet that actually use that field. And this is mostly seen in the form of a pathology that we've called toss precedence bleaching. And what happens here is that routers on the path essentially take the diffserv field and only clear out the first 3 most significant bits of it. And this is how you end up. So if you take a code point, say 46, and you think of it in binary and you slash the first 3 bits and you make them 0, then what you end up with is code point 6. If you do the same for, say, a popular code point like AF11, then it toss precedence bleaches down to code point 2. So this is how you end up with a lot of these very small code points between 0 and 7 in the core of the internet. They seem to traverse a lot better than the rest of the code points because of this particular pathology. This is supported by a lot of data. We've done trace routes between mobile networks, trace routes in the core of the internet from many different vantage points. We've looked at the packet trace analysis. I think I have some slides to delve a bit deeper in these. But this shows up time and time again in all the different kinds of networks we tested. Next, please. Right, so this problem of toss precedence bleaching is actually a huge problem for DSCP code point assignments. Because if you think about it, when you want to assign a new code point, say you want to assign code point 17, you wouldn't really want to do that, because if you apply toss precedence bleaching to code point 17, then what you get is lower effort. So that could be a huge issue because of priority inversion. But the problem is twofold, because it also means you can't really assign these small code points because you have so many popular code points that bleach down to, say, code point 2, then you end up with a lot of traffic aggregated to code point 2. So you don't really want to assign that code point because there's already so much traffic that carries it in the internet. Next, please. And the bug, and next again. Right, so looking at these very small code points, you have 0, which is best effort. You have 1, which is already allocated. 2, as I've said, is kind of polluted because all of these popular code points bleach down to it, so it can't really be assigned or used. Then you have 3, which is reserved. Next. Then you have code point 4, which has a slightly different problem in that it is being set by SSH traffic everywhere. I mean, not all SSH traffic, but the majority of it will use code point 4 also for historical reasons, which precede diffserv. Next, you have code point 5, which is up for grabs. Code point 6 has the same problem as code point 2 because it's on the same column with EF, right? And then you have code point 7, which is, again, not for use. So the situation looks quite bleak, right? Next, please. Now, I've mentioned the data that underpins this. Basically, we first start seeing this in 2015 when we do trace routes within mobile networks. We see that most mobile networks like to remark, but we also see that outbound, at appearing between the mobile network and the general internet, you see toss precedence bleaching happening. We revalidated this from the core of the internet, where we did trace routes to several web servers. And there you quite clearly see the different end-to-end traversal for the different code points. Smaller code points will always traverse better because of that pathology. And we find out that it happens on up to 20% of the paths we tested and in quite a lot of the routers that we tested. Next, please. Right, then we see this again in data that I did not collect this time. This is data provided by CADA. So CADA used to, they don't do it anymore, but they used to provide very large pickup files that have millions, no, actually billions of packets, as you can see there. They made them available to researchers, and basically these are traces of traffic flowing at an internet exchange point. So basically what you can do is take these traces, which are anonymized, but you can look at the DSCP markings on them. And this is what we found. Next slide, please. Okay, I don't know if this is too small to read, but we found that after BE, the traffic flowing in that particular internet exchange, so you see all of the small code points are the next up. So you see DSCP traffic marked with DSCP2 accounts for up to 19% of traffic in this particular data set, and this persists regardless of how you split the traffic or what year the data was collected in, or even across IPv4 and IPv6, you see this pathology. And DSCP2 is so prevalent because, of course, it is what results from toss bleaching of AF11 and AF1021 and all of these popular code points at the edge, right? Next slide, please. Oh yeah, finally, I'm not going to recap the RIPE Atlas test, but you can still see the really cool map there. If you do a test from the edge, you can still see that toss bleaching happens on up to 10% of paths. And this, of course, results in the different traversal rates for high code points versus the low bottom 7 code points. Next slide, please. Right. Okay, so I mentioned this is a problem for assignments, and this is a problem for assignments because recently there has been some interest in assigning a new DSCP code point that has internet-wide scope, right? Because diffserv works in diffserv domains. And so you might think this is not really a problem because why do you need a DSCP to work across the internet? Well, you have to think a bit about it because you can either accept that there are only 8 code points that can make it across the internet, and then you kind of have to think of these as aggregates. But then you kind of accept that toss precedence bleaching is something that happens and that is here to stay. Or you can choose to go the other way and say, no, maybe toss precedence bleaching shouldn't be happening, and then all of the code points can be used end to end, right? Well, we've put all of this data in a draft. I encourage you to go and read it. It's called Considerations for Assigning New DSCPs, and it describes the pathologies, not just the toss precedence bleaching, which is the one I talk about today, but others. So it describes all of the pathologies that DSCPs are subjected across an internet path. But also this data help guide discussion of around the new code point that was requested, or rather a pair of code points that was requested in order to provide like an end-to-end PHP across the internet. So basically the non-queue building traffic graph originally proposed 2 DSCPs, 45 and 5, essentially because of this problem that I described. But then it worked out that only 45 was allocated in the end because people didn't want to risk making the DSCPs in that same column unusable. Yeah, so we don't really know where to go from here. Next slide, please. Because essentially, we don't know that much about who does toss precedence bleaching, because it might not just be old misconfigured routers that do it by mistake. It might just be operators that actually have policies like these. So I have a survey if you are interested. If you are an operator and you use DSCPs in your network, and even if you don't, because this survey will ask you questions about DSCPs, extension headers, maybe even MTU. Please complete this because I would be very interested to understand how people use DSCPs within their networks and see where we go from there, because we might end up making a draft that does make actual recommendations on how to assign new code points rather than just an informational considerations draft that we have now. Right. And that concludes my presentation.
Great. So I'm actually in the queue, and I happen to be first. So, I mean, a lot of network devices still have a very small, like limited number of queues, like 8 queues for interfaces.
Well,
okay,
you
buffer,
have, like,
but they have a number of queues they can buffer into. Yep. And a lot of operators obviously want to be able to prioritize stuff like routing updates. And so sort of if you're going to put those into some sort of yes buffer queue, you're going to have to use at least some of those. And I suspect that that likely means that you're going to have a hard time always with this. And that's me. Tom?
Hi, Tom Hill from BT. Typically, generically, I suppose the problem is that if you're accepting any form of tag like this on a packet from your outside of your domain,
Yeah.
your AS number, your AUT number, it's informing your routers how to deal with that traffic. And operationally, unless you agree it with a third party over in another AS number, you really don't want someone to tell you how to do that without your knowledge. And it can sometimes have regulatory impact. So net neutrality, for example. That isn't to say that everyone's doing this perfectly and wiping everything off the edges. I think the main takeaway from here is that if you're writing anything into those bits, you don't care what's in there in the first place. You're overwriting it carte blanche.
Yeah, but then why overwrite only the first 3 bits? I mean, I'm all for treating unknown or DSCPs that you don't trust and remark them all, say to 0, bleach them. That's allowed by the RFCs, should I say? But why do toss precedence bleaching in that case when you can just do?
It's probably a combination of a lack of knowledge and a lack of nothing is broken. If everything is working, no one has time to spend on this. So.
Okay.
But I find it very interesting that you've done the work and the research, and I'd like to keep some eyesight on this in the future. So thank you.
Thank you.
Jared Mott, Akamai. Just a couple things. First of all, a lot of people get confused, as I was calling out Warren on the difference between queuing and buffering, because most of the hardware does that. Similar to what Tom said, yeah, at the network boundary, you tend to stomp on everything. The other thing is there's a lot of hardware devices where the second you turn on anything, it automatically just bleaches everything because it assumes that you're going to actually configure an explicit policy on every interface, either if it's a permit or not, and it'll just stomp on everything with zeros. And so I think I'm a little bit, I suspect that the reason why only so many bits are touched is because that's all that's programmed in the hardware. Because in most cases, when you've got a hardware-based, ASIC or forwarding chip or whatever, it only looks at those bits, at those first couple of bits, for all the router devices that are in the hardware. And so I suspect that is why it's only writing in those bits as well.
So then is this equipment not configured for diffserv if it's only looking at 3 bits of what is a 6-bit field?
Most people don't configure that. Most people just leave it in the default configuration. And the second you turn on any sort of QoS, like I'm using a really old example, but like the Cisco 6500 that a lot of people use, the second you typed the command MLS QoS into it, it would just stomp on everything. So I suspect it's a combination of several of those things, which is why you're seeing the behavior you're observing. Super interesting, though.
Cool.
Hi, Alistran. As someone who does UDP services for a living, do you see any difference between UDP and TCP behavior?
Could you repeat the question? I'm sorry.
Do you see? I noticed that the measurements mentioned TCP. Do you see? Have you got any measurements using UDP, and was there any difference?
Okay, so this is you can find the details. So the short answer is no difference between TCP and UDP in this case, and you can find the breakdown of the measurements in the journal paper. That is the second one, the middle link.
Thank you.
Excellent. Thank you. Great. Thank you. That was fascinating. And now we have our last and final presentation, unless I missed any, which is going to be either Jeff or Joao talking about Do versus Dot.
Me again. Joelle and I looked at each other and evidently I met. So it wouldn't be an IEPG meeting without the DNS or BGP or both. I mean, it just wouldn't, would it? And you haven't had your daily dose of BGP, but this is your dose of DNS. And this is actually about trying to understand those recent moves to encrypted DNS, which is DNS over HTTPS and DNS over TLS, to what extent they're actually being used today. Next slide. So I'll be quick, there's not that much in it. But if you've been at all following DNS, DPRIVE, I think was the working group, there has been recent areas of standardization in the IETF of DNS over TLS over TCP and DNS over, now this is weird, it was originally over HTTP 2, not HTTPS 2, and then it's become DNS over HTTP 3, almost by collective action, by simply saying, well, it's HTTP and it all gets swept in. So you may have seen it when you've looked in your platforms. Like Android at this point, there is a part of the config screen that says, add a secure DNS resolver by name. And what that actually will do is actually create a TLS association and authenticate the name of that named resolver, and then thereafter use DNS over TLS to query that. So this is in the area, by the way, of stub to recursive. So this is the first hop. There is a parallel effort going on in DPRIVE to do recursive to authoritative. They're still in the middle of the swamp. The other place where you might see this is where you actually don't have a big ability to configure it yourself. And this, the best example I can find is in Firefox, where I think it's about 2, maybe 3 years ago, they decided to adopt what they called a trusted recursive resolver program, where they would take queries made by a client's use of Firefox, and instead of passing it down the platform libraries to do a conventional resolution, would actually do the resolution inside Firefox, going to what they called one of a small set of trusted recursive resolvers, and perform the whole transaction using DNS over HTTPS. So using DOE. Next slide. So there was some evidence that this was around and available, but you know, the number of folk who twiddle with the knobs on their platform is probably fewer than the number of people in this room, because you know, you're going to break something and then you're going to brick your device and then, you know, you're going to feel guilty or something. So in some ways, creating these facilities was never, ever going to change the needle. It was always going to be tiny, unless, a bit like Firefox, it took the decision out of your hands and just did it, where you weren't consulted. If you happened to be in the US and you used Firefox, your DNS resolver started to use DOH and you had no control. Next slide. So hijacked, yes, you can call it that if you want, Jared. So the issue is, thank you, the issue is, how successful are these measures? You know, after all this standardization, does anyone actually use it? Now, if you run an authoritative server, it doesn't help, because stubs don't ask authoritatives. So it doesn't really matter how recursives ask you. You can't see how the stub asks the recursive. So authoritative server data is of no help. Root server data, day in the life, doesn't help. So none of that data is of any use if you're trying to measure this. Now, I can measure me as a stub resolver and you can measure you, but there are another 4 billion, 5 billion odd stubs out there. And I'll readily claim that I'm an anomaly, and compared to the other 4 or 5 billion, you're probably an anomaly too. So small stub data sets don't really help either. And while it would be really good to look over the shoulder of some large-scale recursive resolver operator or some large-scale ISP that does recursive resolution, the privacy of that data is almost absolute. And I can't blame them either. This is really sensitive data. It's what you and I ask of the DNS. And that data is extraordinarily sensitive, and properly so. So while in theory the data might exist, it's very, very difficult to get hold of because of that sensitivity. Next. Accept. Now, there was one provider, Cloudflare, who was desperate to use 1.1.1.1 and one RIR, a PNIC, that had it. And so we came to a deal. We would let them use 1.1.1.1, but for research purposes, we would get to see a certain amount of the traffic, the query traffic, that hits 1.1.1.1. Now, I don't know if you're using 1.1.1.1 that it was you. I have no idea. I don't know who's querying, but I do see the protocol you use to make that query. So I get to see Cloudflare, which is a big open resolver. It's around 4% of users worldwide. So it's non-trivial. Next slide. Oh, I thought there was another thing there. Next slide, is there a? Yeah, no, back one, back two. I was just going to prove that it's 4%. Yeah, that's the one. How did that not get up there?
I don't know.
Yeah, right. Google currently, of the resolvers that people use, operate around a 16% market share. 1 in 7 users believe what Google tell them, because that's the first recursive resolver that offers back an answer that they believe. So Google has a dominant share of the open recursive market area of the globe. But Cloudflare is certainly number 2. And currently its share is around just under 4% of all users worldwide. OpenDNS still has residual use in Quad 9, but you know, Cloudflare is not nothing. It's not as massive as Google, but it's certainly significant. Next. So now we bring back the next point I want to make, that Cloudflare is a trusted recursive resolver. And so this data is loaded with Firefox data that would not be present if you were using the view from your ISP, would not be present if you're using, you know, a conventional recursive resolver. So it's biased and skewed, right? Just remember that. Next. So this then brings us to about the only slide that's really of material context. Cloudflare sees about 75% of queries coming in over UDP. Nada. But the next biggest, and rising very slowly, but rising, is 20%, which is actually coming in over DNS over HTTP, not over TLS, over HTTP. And the number of folk who have twiddled with the knob somehow and using DNS over TLS, slightly under 5%. And in Cloudflare's case, the number of folk who use TCP, either because they got the truncation bit in UDP or they just felt like using TCP, is down at below 1%. So oddly enough, it's DOH that has captured a fair amount in Cloudflare's view of the way in which we encrypt stub to recursive, and DNS over TLS is actually a far lower, about a quarter. Next. So what's the map of DNS over HTTP? The yellower or greener, the larger, the redder, the lower. Now, in some ways, this might be a map of Firefox use. I don't know, I've never really looked hard. But, you know, America, so-so. Russia, a little more. Morocco, is it? Somewhere over there in Northern Africa, reasonable. And, wow, Thailand. Who would have guessed? Next slide. So I think this is all about Firefox and trusted recursive resolvers, personally. Hard to really tell for sure, but in some ways it's not users doing things and not even ISPs doing things. It's just the browser going, I know better than you. Let me go and take your DNS traffic and shunt it over HTTP and deliver it to Cloudflare. Yay. Next slide. So, you know, if you actually have a look at the Firefox pages of DNS over HTTPS, you know, that's the bit in Firefox that says we're going to use DO, not DOT, for this particular program. Next. So DOT, which is not used as much, Where is DOT against Cloudflare used? Almost nowhere except a little bit in Nepal, and next slide, blow me down, Laos. I have no idea. My suspicion is that this is something the ISP is doing and nothing to do what is happening in Laos. But I can't tell you that because I don't know the IP addresses of the folk doing the queries. So I can't map them to network providers, and I can't tell you which network provider has turned this on because that data is quite properly occluded from me. I don't even want to see that data. But what I can say is that what looks to be some kind of ISP thing is turning on DOT in Laos to Cloudflare more than in other countries. And the amount, at least as Cloudflare sees it in Laos, of DNS over UDP is actually in the decline as a result. How much is actually DOE? Well, a lot less in Laos. No other countries like this. It's just Laos. Next. So what can I say about this? Users don't twiddle with knobs. They really, really don't. And maybe that's a good thing. I don't know. I don't run help desks. If I did, don't ever twiddle with the knobs would be my advice to users. I think this is a lot to do with Firefox and possibly bits of Chrome. I really don't know. But certainly use levels are growing. And whether it's completely Firefox or some other way of which this behavior is happening, I don't know. But maybe other apps. DOT is really low, except in Laos. No idea. And the relative use levels of DOT globally are declining, not growing. No, fascinating. Next. That was it. Any questions that I'll attempt not to answer?
Jelinkova, Jeff, I think the problem with DOT is it's much easier to filter by an ISP. And I know about at least one ISP, which basically blocks DOT. But obviously, it's much harder for them to block HTTPS. So maybe it's one of the reasons we've seen less DOT than
So there are
anything.
two holes in the dike, and I can poke my finger in one, but not the other. So that's the problem solved, right? Yay. It seems a bit crazy, but you're probably right. But this industry has a track record of crazy, doesn't it? No others? Thank you very much.
Awesome. Well, thank you, everyone. That brings us to the end of today's IEPG meeting. Don't forget, there will be another one of these next time we meet. So if people have anything they would like to present, please let me know. Also, another shout out for the technology deep dives, which is tomorrow starting at 8 a.m., which, yes, I realize that's terrifyingly early for most people. But, well, maybe jet lag will help you wake up earlier. It was the only time that was available. Thanks all.
We have to go back to Argentina when all the meetings started at 10:30.
No worries. Hi, how are you? I think this went off fairly well. It's interesting how things change. Like, it used to all be DNS and all be BGP. Now it's all extension headers. I don't know what it'll be in 5 years.
And you had to write it all by yourself.
Yeah, I don't know where Chris. I guess he was asleep. He's not here. Life is good for you?
I just came back from right meeting last week.
I wasn't there. I was at Nanon.
Oh, yeah. I heard some people actually did.
Yeah, I was going to. There's also the ICANN guest set. Yeah, that's a lot. There's also the ICANN guest set meeting. So, yeah. How was Frank? Good. This is still on as well, I think.